Hello everyone. So today I'm going to talk about the Wilson's theorem. So the statement is as follows. Let's say that we have a prime number p. So p is prime, and we need to prove that the number p minus 1 factorial is congruent to minus 1 modulo p. So let's consider this number p minus 1 factorial. So we know that this is equal to the product of the numbers 1 multiplied by 2 multiplied by 3 and so on multiplied by p minus 1. So we notice that these all numbers 1, 2, 3 and so on, p minus 1, their residues modulo p. So like they're all residues except 0 modulo p, and we know that the residues modulo p for a prime number p form a field, and this means in particular that each residue except 0 has an inverse by multiplication. So inverse by multiplication means that so like for each x such that x is not congruent to 0 modulo p, and I'm going to stop writing modulo p because all congruences are going to be modulo p. So for each x that is not congruent to 0, there exists x to the power minus 1 such that x multiplied by x to the power minus 1 is congruent to 1 modulo p. So this is the inverse. So the product of the number and its inverse is congruent to 1. So we can use this property to basically to divide all numbers in this product, to divide all of them into pairs. So if we pick some number x in this list, then we find a pair for it, that is x to the power minus 1, and so this whole product would seemingly be divided into pairs of number and its inverse, and so in each pair the product would be congruent to 1, and it seems that then the whole product would be congruent to 1, right? Well, not really. So this argument actually doesn't work that way, and the reason is that the inverse can be the number itself. So like x to the power minus 1, it might be that it's congruent to x, and then for such a number the pair to this number would be this number itself, and then we can divide it into pairs. So so this argument doesn't work directly, but we can investigate what are such numbers that would be paired to themselves. So if we assume that x is congruent to x to the power minus 1, so what, like we need to find all such x. So this we can rewrite as, if we multiply by x to the power minus 1 both sides, then we get x squared is congruent to 1. Then we can move 1 from the right hand side to the left hand side. So it follows from this that x squared minus 1 is congruent to 0. Now congruency to 0, it's the same as divisibility by p. So like if a number is congruent to 0 modulo p, it's the same as it is divisible by p. So x squared minus 1 is divisible by p. Now we can rewrite the left hand side again. So x minus 1 multiplied by x plus 1 is congruent to 0. Now we can apply Euclid's lemma. So this lemma states that if a product of two numbers is divisible by a prime number p, then either one of these number must be divisible by p. So from this we conclude by Euclid's lemma that either x minus 1 is divisible by p or x plus 1 is divisible by p. And this we can rewrite again as so x is congruent to 1 modulo p or x is congruent to minus 1 modulo p. So basically we found the two residues that that don't have a pair, that are paired to themselves. So it's 1 and minus 1. Well, minus 1 is not actually a residue, but like it belongs to the residue class of p minus 1. So basically, yeah, and by the way, so this all the implications were only in one side, so we need to verify that the other side, the implication to the other direction also works, so that x congruent to 1 and x congruent to minus 1, they indeed satisfy that x to the power minus 1 is congruent to x, but this is like we can verify it directly. So basically we have two special numbers in this list. It's 1 and p minus 1. They would be pairs to themselves, and all the other numbers, like from 2 to p minus 2, so the other p minus 3 numbers, each of them indeed has a pair. And so for them, the argument is divided into pairs, it would work. Okay, so let me remove everything that is. Let me remove what we don't need anymore. Okay, so now this product would be congruent to what? So first we rewrite the special numbers 1 and p minus 1, two special numbers. Then for the rest, p minus 3 numbers, they are divided into pairs of basically x and x to the power minus 1, such a product, and each in each pair, this product would be equal to 1. So therefore the whole product, like everything here, it would be congruent to 1 multiplied by minus 1. So p minus 1 is congruent to minus 1. And the rest of the product would be a bunch of 1s. 1 multiplied by, so on, multiplied by 1. And so this would be basically congruent to minus 1. And this concludes the proof because that's what we needed to prove.